Okay, so I want to show you just a couple of things that are going to help you with the problem set today. So obviously you already know that if the horizontal component of a vector is 3 and the vertical component is 4, then the overall magnitude of the vector is 5 because of the Pythagorean theorem. But let's talk about some interpretations of what this could mean. What if this is actually describing a ship? So we've got my ship that looks like this. It's a sailing ship. And I'm sailing straight north at 4 meters per second. But then there's a wind that's blowing so that my ship is also moving in this direction at 3 meters per second. So even though I'm trying to just drive straight north, the water is actually moving me 3 meters per second this direction at the same time. What is the actual motion of my ship? The actual motion of my ship is this same this same kind of diagonal vector. So I'm moving at 3 meters per second that way, and at the same time 4 meters per second up. And so I know that my overall speed in this diagonal direction is 5 meters per second. So what I'm getting at is you can interpret all of these as speeds if you want. 3 meters per second, 4 meters per second, 5 meters per second. But they're all in their own directions. Another interpretation of this would be if I launch an object at a certain angle. So let's say I launch something at a 45-degree angle at 10 meters per second. Breaking apart that speed into horizontal speed and vertical speed that are separate from each other. So if I launch it at an angle at 10 meters per second, that means that the length of this diagonal is 10 meters per second. But if I want to know how far is it going horizontally and vertically, that's like these two separate components. So I would have 10 meters per second times cosine of 45 degrees for the horizontal, and 10 times sine of 45 degrees for the vertical. And you should know both of those are root 2 over 2. So that's 10 root 2 over 2 and 10 root 2 over 2. And if we're in outer space where there is no gravity, then it's just going to keep going this way forever. If we're in an environment with gravity, then it's going to make a kind of a parabolic trajectory. But the parabolic trajectory is just the vertical component changing. So as it moves at a constant horizontal speed, the vertical speed will decrease until at the peak of its trajectory, the vertical speed is 0 because it's not moving up or down. And then the vertical speed will become negative to make it fall back to Earth. But this entire time, as it's going up and down, the horizontal speed is just still the same. So the horizontal speed will never be anything different than this, unless we decide to add other forces like wind resistance. Okay, last of all, let's think about speed of something that's following like some kind of crazy trajectory. So let's pretend that I've got a vector v that's got like a very complicated equation, something complicated, and it's tracing this thing out. So how could I know how fast it was going at a particular moment? And sort of like, what does the speed look like if I was going to sketch it as a picture? So let's pretend t equals 1 is right here. The speed that I'm going at, you can imagine, what if right at that moment I stopped turning and I just kept moving in the same direction I was moving in right at that moment? What it would look like is it would look like a straight line. So if I stop turning and I just start going straight, that's the direction I was going in. And then let's look at a little while later. So at time equals 1.2, I'm right here. And same idea. If I stop turning and instead I just keep going in the same direction I was moving in at that moment, it would be a straight line. So the lesson here is velocity vectors show the speed and the direction that we're moving. And right now we're not talking about speed yet, we're just talking about direction. And the direction is always a line that is tangent to the curve that I'm traveling along. So what about speed? So we've got two different directions, direction here, direction there. Speed is about the length of the velocity vector. What I've sketched here is maybe unrealistic. But this was like the magnitude of v at time equals 1. So a longer vector would mean that at this particular moment, it's going faster in that direction. But it's not going to go all the way to the end of the vector because the length of this vector says how far will it go in 1 second. But before 1 second, we've already started changing the direction we're moving in. So it doesn't get a full second to travel along that velocity vector all the way to the end. Instead, it travels along this velocity vector for, a split second, and then the velocity, and now I'm in a different place, and the velocity vector has changed, and then I travel a split second in that direction, and I'm at a different place, and the velocity vector has changed. So you got to imagine as time is moving on, I'm moving along the velocity vector, but the velocity vector is also kind of changing. Okay, so what if we wanted to actually calculate the velocity vector at a particular moment? So in calculus, there's a tool for this, and you're going to spend like a lot of time doing this in calculus. But for us, we can approximate the speed at a moment using just what we know about speed. So speed is change in distance divided by change in time. That's always true no matter what. So what if we've got some very complicated path, but we want to know what speed are we moving? All we've got to do is choose two times that are a very, very small amount of time apart. So what if we have time equals 1 and time equals 1.01? Is that small enough to be a good approximation? It depends on the timescales of the application you're thinking about. But for us, that seems fine. So here, this is a change in time of 1/100th of a second. So I can plug in time equals 1 to the equation, and it's going to give me, some particular coordinates. So maybe I'm at, like 100, 102. And then I plug in time 1.01 into the complicated equation, and it gives me something else. So I'm at like 100.123, and then I'm at 102.004. So like I've moved a little tiny bit. So all you have to do is use the Pythagorean theorem to find the distance between these 2 points. And then that's going to give you your change in distance. And then you divide that by your change in time, and that's going to tell you your speed, which is the same thing as the length of your velocity vector. Here, if we wanted to, we could like zoom way in on just this little bit. And in just that little bit, we've got, our path curvature there. And we've got our time t equals 1. But then, a split second later, we've got t equals 1.01. And so whatever distance we've traveled, you can break it down into a little tiny delta x and a little tiny delta y. And even though I'm traveling in a curve, if you have a small enough distance along the curve, then the straight line is a pretty good approximation of the arc length of the curve there. And the straight line, of course, is the hypotenuse of your triangle. Okay, that's everything that's required for today's problem set. Oh, one last thing. If I wanted to calculate the direction that I'm moving at here, once I know what the delta x and the delta y are, then you can use the arctangent of change in y divided by change in x to find whatever that angle is. And just remember, like in this case, the angle that I calculate here actually gives me my heading. If I was pointed in a different direction, the arctangent of delta y over delta x might give me a different angle, and you would have to use reference angles to adjust it correctly to give the actual heading that we're traveling in. Okay, good luck on the problem set.